Hello, everyone. Just a couple minutes here before we begin. I'll get my screen shared and we'll begin here real shortly.
Okay, Harold.
All right, well, welcome everyone. Today here we have our webinar on, I guess our first webinar in our series about statistics and ARM. So today's session really just an overview. I really won't be diving into the ARM program as much, but more talking about the general things that we will be covering here in the following sessions. So today primarily working in PowerPoint and talking about the different topics, and then the following sessions, we'll have 3 of them, will be exclusively in the software and actually doing those steps and giving some examples and discussing things in those sessions. So a couple of housekeeping items before we get going. First of all, if you would have any questions as we're going through today, feel free to send them through the chat. It's a great way. We'll have a fair number of participants. It looks like our list is growing as we're going right now as well. So that the chat works really great for those questions. And I'll just kind of keep an eye on them. So, as if they're timely, kind of right where we're talking about that topic, I'll try to stop and cover them right away. Or also I like to save a little bit of time at the end of the session too, if there's questions that are, slightly tangential or such. I always like to save a little bit of time there as well. So the other item of housekeeping is the recording. So we are recording this session as we do all of our webinars, and we will post them onto our website. And so something new we've been doing this year, we do post them out to YouTube, so you would be able to view them there, and we have an archive out on our webinars page on our website. But we are also linking through our LMS, our training portal. And so as you may have saw with the registration, if you've indicated that you're interested in that, go ahead and make sure you get signed up. And you can get that through our website on our training and tutorial. You can go and sign up for the LMS or use the link that we sent in your email. And so if you have an account here in the LMS, then we will upload this recording to that portal and link your account to show that you participated. And if you want a certificate to kind of show you participated, you can get that within the portal. You would just go into the session name that's been linked to you, and you just kind of confirm that you did that, and it'll give you a certificate as well. So, all right. Well, with that, I guess we will dive in. And as I said, for any of you that joined us late, here we are really covering an overview of our statistics with ARM. And so today we'll be in PowerPoint, and then the next 3 sessions we have will be about data confirmation, data review, and the reporting aspect, and those will be exclusively in the software. So we'll dive in here with just a real nice overview here of research in general and as it pertains to ARM. And so, you know, the goal of research is often to determine whether treatments of interest perform differently. And, you know, the choice of treatments, it can be different products, different formulations, or different rates of application, all different kinds and types. But anyway, we want to know if those treatments can be distinguished from one another, if it's their effectiveness, you know, safety to the crop, or their cost. Sometimes you might even hope that the performance is indistinguishable if your product is cheaper. So research trials are then performed to obtain observations of the treatment performance. We call them assessments or ratings in ARM. But the question is, are those observed differences due to the treatments or due to random chance? And that's where statistics comes in, namely the analysis of variance. But of course, you shouldn't immediately jump to the analysis after recording the data. So data confirmation is really important to catch any outliers and issues with the assessment before you analyze. So, you know, thinking about an outlier really breaks all 3 assumptions of ANOVA. You know, it can trigger skewness and you know, as a result, the non-normality, non-additivity, since outliers are not distributed equally, and heterogeneity of variance. So, you know, we'll kind of dive into those specific assumptions a little later, but that's really the you know, one of the main reasons why outliers really, you know, kind of mess with the data. So, you know, how can we avoid these problems? Really, you want to keep detailed records of the site and the assessment and confirm the data as soon as it's taken. These are kind of, you know, real good benefits of the TDCX, the tablet data collector add-in that we also offer. And of course, you can also, you know, identify an acceptable range of values before the data is taken. So you have an idea as you're going into it, what is reasonable, so you can see when that is not occurring. And so this, you know, this whole topic here, that data confirmation, that's really our focus for session number 2. Next week, Tuesday, we'll be, you know, working through the steps and tools in ARM for this data confirmation step. So agriculture research is always subject to variation from a variety of sources. So we perform an analysis of variance on the data. You know, statistical variance is a measure of how spread out the data is about its mean. And we also call this ANOVA or AOV. The analysis of variance dissects the variability in the recorded assessments. There is controlled variability from the treatments and the blocking structure, and the experimental error is uncontrolled. So essentially, we're considering that if the observed differences are due to chance, then the variance between treatments must agree with the variance within treatments. Kind of really where it all boils down to. And so here's an example output of the AOV analysis. I just kind of took an example trial with 5 treatments and 4 replicates. We'll just kind of break down each of these components here. So the first one is the degrees of freedom. This one's a little tricky to define, but it's really the number of values in a final calculation that are free to vary. So with variance, the degrees of freedom is n-1. So for 5 treatments, you have 4 degrees of freedom. And really the mean is calculated to determine the variance. And so that's why you're subtracting that one off of there. The sum of squares represents the amount of variation in the data, and it's split up into each source listed in the table as the different rows. The mean square is the sum of squares divided by the degrees of freedom. We're basically taking the amount of variation and divide it by the degree to which it can occur. Then we calculate an F ratio, which indicates the level of variation from that source compared to the random variation. The larger the ratio is, the more likely that variance from this source is not due to just random chance. So to quantify this, we calculate a p-value, the probability that observed differences in treatment or block, whichever source you're looking at, the probability that the observed differences in treatment means could have arisen by chance. So a low p-value, typically less than 5% or whatever alpha level that you're running at, indicates that we can be confident that there are real differences among treatments. Whereas a high p-value, like here between blocks, that indicates that there is no evidence of a real difference among blocks in this case. This could be because there is no real difference or that the differences are too small to detect. So to summarize, the AOV analysis breaks apart the variance of observations into sources and then calculates a p-value as its end result. So, really a one-liner there to remember is a p-value is a probability. That AOV p-value is the probability that no differences in treatments exist. So a p-value of 0.04 means that we are 96% confident that there are significant differences between treatments. But we are not done yet. We need to know which observed differences between treatments are significant and which are not. So the AOV analysis we just outlined does not provide an answer about which observed differences in treatment means are significant, just whether there is evidence that a significant difference does exist. So really the next step in the analysis is to run a mean comparison test. Also known as multiple comparison test or mean separation test, these compare treatment means to determine what differences are significant. ARM has a variety of mean comparison tests to choose from for different situations and different research types. These four are the most common ones: the LSD, Duncan's, the Student Newman-Kuhl's, and Tukey's HSD. Common question is, well, which one do I choose? So it's not a political discussion, but tests can be classified by how liberal or conservative they are, meaning if they are more likely to report a false positive, which is your type 1 error, or a false negative, type 2 error. You should also consider the penalty of failure for the study. When a trial is used for registration, then a more conservative test is appropriate. But for a screening trial, it's all about potential. And so you'd be more likely to lean towards the liberal test, because you just want to find any potential, any chance out there, and later trials can help whittle down to determine for sure if some of those differences you see are real or not. We do have a handout that just kind of talks about some of these items, and on page 2 of this handout, it goes into a little more detail about some of those mean comparison tests. If you're not quite sure, a lot of times it's kind of the combination of this type of research and in your industry, your research you're doing. There might be one that's just generally accepted, generally used more, whereas if you're not sure, there isn't kind of a go-to standard in your industry, then some of these other ideas here we just presented are a good way to decide what is most appropriate. And I do see a question, kind of more of a request for the Scott-Knott test. So that's another mean comparison test, and we have heard that request before. I think it's heavily used in Brazil, if I recall. So that one is on our radar. So thanks for bringing that one up. That's something that we certainly could add in the future as another one, most likely in your area / research. Again, if there's any items that you would need, we certainly want to be serving the industry. So thanks for that comment there. All right, so let's show an example here of really how a mean comparison test works. The specifics for each different test might vary a little bit, but the basic concepts are the same. And so I think this can be illustrative, at least of in general, how those tests typically work. So first, a test statistic is calculated to perform the comparison of the means. So I'm going to use the most simple mean comparison test here, the LSD. And so we just have a flat value for the LSD. In this case, it's 5.49 for this data here that you can see on the right. So then we will compare the means using that statistic. If the two means do not differ by at least that LSD value, then they are not considered significantly different. Then letters are assigned such that the means with no letter in common are significantly different according to the test. So here we can say that there is evidence that treatments 2 and 5 differ because there is no letter in common, but there is no evidence of a difference between treatments 4 and 5, since they both have the letter A. Real quick, I used LSD here because it's kind of the simplest example to illustrate, but it probably deserves a little bit of a warning as well. That this, the LSD test is really designed and intended for specific comparisons chosen before the data is collected. So if you're using that to make more than one comparison, kind of like across the whole trial, as we showed in this example, the true significance level becomes much larger as the treatments increase because there's more pairwise comparisons being made. So that's, and LSD is really the most liberal of those tests that we had talked about before, and that's kind of part of the reason why. So just take care if you are choosing to run the LSD, especially the longer your treatment list gets, the more comparisons you're running, and really that true significance level for the test starts to balloon. You're going to have more likely to have false positives as you go. So there is kind of one big elephant in the room here from all of this analysis, and we kind of alluded to it earlier. And it's that the ANOVA has some requirements or assumptions of the data that it is run on. And so if these requirements are not met, then the results of the AOV analysis can't be relied upon. So what are these assumptions? The first one is homogeneity of variance. Really that the variances within the treatments are approximately equal. If a treatment is much more variable or much less variable than the others, the ANOVA will not work. So to determine if this is the case, we can look at a box whisker graph and run a test for homogeneity of variance. Levine's is kind of generally chosen, but Bartlett's is also an option. The next requirement is that the data is approximately normally distributed. If your data is not bell-shaped, then you can't use the same p-values in the analysis. As Peter, our statistician, would say, it's just math. So tests for this include skewness, kurtosis, and Shapiro-Wilks. We all have available in ARM. Finally, the last two assumptions are independence of errors and additivity of treatment and block effects. These are a little bit harder to test, but generally are not a big issue in this type of research. The biggest thing here is to not introduce bias in the assessment, like edge effects or subjective ratings being influenced, things like that. So as far as ARM is concerned, the assessment map, kind of a heat map, if you will, that we'll get to see next week, that can be useful to maybe detect some of these things if they are an issue. So again, this is really, these ideas here are about the data review component is really kind of that next step. So our next session we'll be doing on the data confirmation. The following one will be about this topic here, that really the data review. And we'll look at each of these tools that's available in ARM and how to test for these assumptions of ANOVA. And so then, the next question is, what happens if these assumptions are not met? So we do have data correction transformations that are designed to correct the underlying distribution of the data without affecting the results. And so kind of the main ones that are used, first one being the logarithm transform. And so that's good to use for counts of things that occur in clusters, or from kind of a distribution standpoint, it's really when the data is following kind of a log normal distribution instead of the normal bell-shaped curve. The square root transformation, that's really good for counts of things that occur at random or rarely. And typically your data in that case follows a Poisson distribution instead. So maybe you have a lot of zeros, lots of zeros and ones, and then every so often you have a 2, 3, 5 type of thing. And you really would never have the bell-shaped curve in that case. A third one is the arcsign. Arcsign square root percent is the full title there. And that's really great for percentage data. A lot of times you might end with a binomial distribution in that case. So really each of those you kind of have their own little niche kind of category type of data that can be used on. And really the nice thing there is that you're applying that transformation to all of the data points. So it's not fudging the data, it's taking every single data point, applying that same transformation to it, so that way the distribution of the data then that we analyze, all those transformed data, is now something that the AOV can actually work with. So we're still the same results essentially, but we want to run the analysis on something that it can make sense. So another tool in our toolbox here would be spatial models. And so really the idea here, spatial models try to recover information about hidden variables across the field. So in ARM, we have 3 trend models and 4 nearest neighbor models that can be used in ARM. These are a little less common to be used. Typically, you would only use these when your blocking design fails. So the typical randomized complete block You try to anticipate where the variation may be, and design your replicates to be set up so that way each replicate is fairly homogeneous. Well, then once the trial gets going and we can look at the results, maybe we find out that no, there was a different variation that across that trial that really was not explained by our blocks. And so really at that point, the spatial models are a way to kind of toss out the blocking and try to recover as much as we can. Kind of making the best of a bad situation, if you will. So isn't something I would say you would always want to dive into and try to use in the data review. And the third one here is non-parametric statistics. And really that's actually totally different technique than the AOV. And really the idea being, let's just toss out AOV and all of its assumptions. If we can't make these assumptions work, let's not even try AOV. And instead analyze the data by ranking the values. And so that's really the non-parametric statistics are focused around the ranks instead of the means and the variance. Nice thing is you can still run a mean comparison test on the mean of those ranks. So we still can kind of fit this right into our same AOV report, which we'll see on our third session. But instead of the raw data that you're using to summarize with the mean comparison test, we actually rank the data and use the mean of those ranks as the mean to provide to that comparison test. And so that that one again, it's kind of like once you've run out of fixes, try the data correction. If there's no transformations that fix those assumptions, we can't get the data in a spot where the AOV can be trusted. Let's just pivot and try something different. So that's really the idea there. I have a couple of questions here. The first one, if one plot or replication does not meet the assumptions of AOV, does only that plot or replication need to be transformed? Or does data transformation need to be applied to everything or nothing? So kind of the back half of that question, certainly the transformation is done across the whole assessment, that whole data column in ARM, really out of fairness that you would want to apply the same the same calculation to every data point. So that way you're not changing the results. And really then to that the first half of the question, really the assumption of AOV is those assumptions are looking at the whole data set all as one. So there's not so much a single data point or a single replicate that would be non-homogeneous or would be skewed, for example. If you think about the bell-shaped curve, you really are referring to all of the data points in that data set, in that assessment. So you would have one of the larger values can certainly be part of the tail of that bell-shaped curve. And that one value you wouldn't throw out because then you wouldn't have a bell-shaped curve anymore. So really, you really aren't necessarily looking at individual components of the data set, but you look at the entire assessment, and that's what the AOV is looking at, the entire assessment as a whole. So those fit those assumptions. And we'll kind of show some of the as we talk about what to do when we fail to meet these assumptions. Historically in ARM, we had a tool that would come up as you're generating your report, and it would suggest some of these data corrections, and it would also suggest potentially dropping a treatment or dropping a replicate, and that maybe is kind of tied to your question a little bit. But really, I think that's a little bit of an extreme thing to do. Technically speaking, it can work. So that was part of what Aaron was doing as well. If we throw out treatment number 2 and then run the test for our assumptions of AOV, do things get better? And then, the idea being, okay, this isn't great. Of course, you want all of the treatments here, but if we can't do anything else, then maybe it's better to at least try to do something with the rest of these treatments. Really, that was before we had the non-parametric statistics option. And so I think it makes more sense logically as you kind of look at the list here on the screen. Okay, if the transformations don't work, well, instead of trying to throw out some treatments that might be pretty important for our objectives to see if we can do something with it, maybe it makes more sense to just run the non-parametric statistics instead. So that's maybe a little bit soapboxy, but that's where we've kind of transitioned away from that old tool that's in the report stream for some of those recommendations. And now, as we'll see in day 3 of this series, we'll show the column diagnostics panel, and that has kind of this list here on the screen as really the toolbox there, and we don't consider tossing out a replicate or a treatment. So great question. Sorry if I got a little sidetracked as well, but a great question there. Next question about the nearest neighbor. So I don't have a very good example right now, but I could dig up a little bit of an example for another time, perhaps. I'll admit that the spatial models, I can't say I am particularly well versed in. And I don't think they usually make it into our kind of simple examples as we demonstrate this, but it's definitely something that's becoming more common. And so I'm just kind of making a note here for myself, whether we can squeeze it into the data review session, which again, that'll be kind of day 3 for us, or it might be easiest for an email. I could look up your email and send you some information that we have on the nearest neighbor. So I'm just jotting that down for myself, the nearest neighbor example, because I don't think we'll have time on the data review day. A little hard to squeeze in an hour. All that I want to cover in that one session, probably of the 3, is the hardest to go with. But certainly we do have some examples to kind of show, or at least visualize what you're doing there. But overall, as I understand it, with the nearest neighbor spatial model, you're looking in, kind of at each plot, and you consider what the assessment values are nearest to that one plot, and start to make some estimations about the variability there across the field. And again, kind of the whole idea with the spatial model is, okay, we're going to toss out the blocking that we attempted to do, and we're really going to see if we can get a feel for the variation that was out there based on the assessment values we have. And yeah, I'm not too strong in the numeric statistical what's actually happening behind the scenes there, but that's really what's happening there. And so the trend analysis kind of looks across the field, whereas nearest neighbor is a little more localized. Okay, here, if we're considering plot 202 and what adjustments we would maybe need to make, we're looking at just the plots right around 202. So 201, 203, 102, 302, just those nearest plots next to it, and considering that information when we think about what adjustments we would make spatially. So that's really the idea there of those spatial models. Then the next question here, whether we have the ANOVA. And is that the analysis of covariance? If I'm remembering right, we currently do not have that offering in ARM. I know our Peter, our statistician, he's got some things cooking in the background of wanting to bring in some more, covariate analysis and mixed models are some of the code words that I'll admit I don't know a whole lot of the details of, but I hear him talk about it a lot. So I know they're kind of on our horizon to bring in to ARM, because really that's where the industry is going. And we've got so much more powerful computers nowadays than we did even 10, 20 years ago. That a lot of these analysis, it's much easier to be able to do those analysis. And so we're kind of trying to keep ARM modern and bring those analysis into ARM. But at this point in time, no, I can't show you a spot in ARM where that would be, but hopefully soon. So yes, we do not yet have mixed models. I think we're getting closer. I'm pretty sure. Like I said, Peter, pretty much anytime I'm around Peter, he ends up saying one of those two terms, either covariance or he says mixed models. And so I know it's on the horizon. It's just a matter of getting all those pieces. There's so many things to consider in some of those statistical tools and features, because ARM isn't just the statistical output, but then we also have to kind of work backwards and say, if this analysis is available in the report, what implications, what things should we have on our trial map or in our design settings that matches that, so it ends up being quite the project to get everything combined. But yeah, for sure that's at near the top of Peter's list, at least as far as what we want to get in ARM. The complexity, of course, I'm not a programmer, so I never like to promise or guess as to how easy it is to bring it in. But it's great. It's great to hear the comments that it's definitely wanted. That helps kind of confirm our guesses that it's needed and wanted. I'm hearing from you guys that it definitely is. So that actually, I'm going to make a note for myself just to check in with Peter to see, let him know that it's definitely something this group is excited for, and if he had any further information that I can pass along, then I'll try to have that available here for probably session 4 when we're talking about the reporting. It's probably when it would make the most sense to bring that up. So yeah, great questions. This is actually kind of the end of my presentation. So I appreciate the questions and the conversation. Make sure I didn't have another slide hiding here, but yeah, no, that was all here. So and any other questions, definitely feel free to pop them in there. I appreciate the conversation thus far. Again, today's a little short, kind of the overview of what we're going to cover here in the next coming sessions. Really like to set the framework. When I was first learning ARM and kind of the different tools in ARM for this data processing as a whole, that was one thing I noticed is it kind of lumped everything together as data review. Once you put the data in, everything after that was data review. And I was always a little confused by that. So I really like to try to make the distinction, because there's different phases in there. It really isn't just data review. And so that was the structure of our sessions is pretty designed in such a way, and I wanted to make it clear in the presentation as well. Really, there's 2 separate steps. Once you get the data in, is you want to confirm what you've typed in, of course, just for accuracy, that you type the numbers in right, but then also to see that the assessment was done correctly. And so you're just looking at the values, not with any analysis in mind, but just to make sure that the data is in, the assessment was done fairly, correctly, and there were no errors that entered in there, whether it's a typo or things like that. So that's really the data confirmation. And the sooner you can do that to actually take in the data, the better. So that way you can catch those things. And we'll talk about more of that in the next session. And then really you're on a different step in that data review where you're thinking about, okay, now we've got the data in here. What do we want to do with it? We want to analyze it and see, if our objectives have been met. We need to prepare the data for that analysis. And so that's really the second step, the data review. And then of course, the final step is let's run it through the analysis. Let's see the report and what we get. And that fourth session we'll kind of show a lot of some of the common questions that we get. There's different options. There's about 1,000 reporting options in ARM. So we'll kind of try to highlight some of the big players there that you'll want to look for, and some of the common ones people get tripped up on, that I want this report to look different. Here's the option that you can go find. And so I see a question here about doing the analysis in ARM. And so yeah, the non-parametric analysis and the nearest neighbor here, we'll show that in session number 3. So again, I believe it's next Tuesday, we'll do the kind of data confirmation. The data review will be the non-parametric analysis and the nearest neighbor. But the short answer to how to do that is the ARM action codes. There's just a row in your assessment header where you're describing the assessment. We have that special action codes field, and that's where we can tell ARM, essentially give ARM instructions for what to do in the analysis. So that's really the nice thing, is that we're not going in and changing the data values that have been typed in. We're not recalculating information and suddenly the numbers are changing based on these choices, but instead the data remains just like we typed it in, and we're just putting in some instructions into that action codes field. So when ARM does run the analysis, it sees those instructions we gave. For example, run this non-parametric analysis. So for this one data column, don't do AOV, do the non-parametric. And so you put in the AR action code for that one. And the nearest neighbor, the spatial, it's the same thing. Each one of those different spatial models have their own action code that go in, and that's really the instructions for the analysis, instead of having a separate data column with those numbers or anything. So great questions. All right, and any other questions? So when it runs the ANOVA, does it include the two-way analysis? I'm not quite sure on that. Not quite familiar maybe with the two-way analysis. Comparing with JUMP, I would say if you wouldn't mind maybe sending us an email, that would be pretty helpful. If you could just send us an example, probably your trial, and then that output with JUMP versus your output with ARM, just to say, okay, these numbers are different in JUMP compared to ARM, and we can kind of help you compare those two. Sometimes it's just an option in ARM. Oh, I think you're running this type of analysis in JUMP, so here's the option to do it in ARM. Sometimes it's a little more complicated, and we can kind of dive into the specifics there. Yes, so in the next, it'll be in 2 sessions, really, the skewness and kurtosis. We'll look at that. So those 2 are part of the tests for the assumptions of AOV, specifically the normality. So we'll show those tests. They're involved in the data review. Very good. Well, we have a little time before the top of the hour. This will probably be the only session that runs short. The rest of them, I get talking, and we have so many things to cover. So it's harder to squeeze in. But I'll hang on here for some questions. I'll type in my email address here to send in a second. But I do want to let everyone else go if you have another meeting. Or some of you might be closer to the end of the day than it is here in the US. So thank you all for joining us, and hope to see you here in the next week or two with our next few sessions. So feel free, if you do have more questions, to chime in to the chat, but we'll let everyone else go if they need to. So thanks again, and hopefully we'll be seeing you soon. Here I'm just entering the email address. That's our general support box. That's usually kind of the best way to get a hold of us. Typically, I'm the one that reviews that one, but if I happen to be out on vacation or something, then there's always someone else there to answer it. So that's the best way to get a response. And if you just want to drop us an email to remind us you had some questions about the nearest neighbor, then I can provide some more information. So thanks, everybody.